Good morning, good afternoon, good evening, depending on where you're located. Very happy to be with you here today to talk about challenges of size, differences between small and large software projects. Thanks for joining me. I wanted to make some introductory remarks before we really get started. My name is Steve McConnell. You might know me as the author of Code Complete or my more recent book, More Effective Agile. For our purposes today, I think the role I'm really playing is CEO of Construx Software. And the reason I'm playing that role, or the way I'm playing that role, is through these Lunch and Learn programs. Back in 2009, my company launched a SPEAR program during the recession. And the purpose of that program was to provide training for workers who had been laid off by tech companies. That was a pretty popular program, and we felt good about being able to give back to the software community that had been supporting us so well. This year, we've launched the SPEAR 2020 Lunch and Learn program. We are aware that lots of people are working from home. Hopefully, everybody's still getting work done and being productive. But we thought this might give you a chance to participate either individually and just take a break from your other activities, or ideally take the program with your team and then give you something to talk about virtually online with your team. And maybe even use this as an opportunity to take a step back from your day-to-day work and think about challenges on your projects and in your environment, and try to see if there's a way that you can make use of this time to actually improve. My vision for this is that if we can create a community of software professionals who are working from home, then we will have done a good thing during this period. This program will be ongoing through the end of April. We have next week's Lunch and Learns posted on our website. You can check that out at the address below. Please share the program with your friends, share the link with your friends, and I hope you're able to take some of these sessions and have good discussions about them. So let's go ahead and dive into the topic. You can type in questions throughout the event. There should be a pane on your screen that allows you to do that. I will take a look at the questions from time to time and see if there's anything I can answer as we go. Otherwise, and if I don't get a chance to do that, I'll make a point of doing that toward the end of the presentation. I should also say one issue that we've run into is that people hit the space bar, and that can pause the presentation. So if the presentation looks to you like it's frozen, make sure you haven't hit your space bar and hit it again, and it will unfreeze the presentation. The outline for today's Lunch and Learn is I want to spend a little bit of time introducing what I mean by the topic of size. I want to talk about when size becomes an issue for software projects. I want to touch on the very important and I think central issue of size, which is the non-linearity of software size issues, and then give a couple of ideas about how to attack size. And given the length of the session today, we're not going to get into an exhaustive treatment of size, but hopefully, especially if you haven't really been exposed to all the ins and outs of how size affects software projects, this could be a good way to get those thought processes started and maybe build some awareness of why you've seen the differences maybe that you have between trying to work on small projects versus trying to work on larger projects. So this lecture is based on my 4 factors life cycle model, and in the 4 factors life cycle model, the factors are human variation, which has to do with how much variation there is between different people doing the similar kinds of work, defects, another key topic, uncertainty, and size. I really believe that size is in fact one of the most important 4 dynamics to understand. If you happen to have a chance to take the Lunch and Learn session earlier this week, that was on uncertainty, but this session is on size, which is another one of these really key factors. And I think that what I find is that people routinely misunderstand the role that size plays in software projects. There are many assumptions that seem kind of natural and intuitive, but actually turn out to be wrong when thinking about size. And this happens in some fairly prominent ways. For example, these days we're talking a lot about agile scaling approaches. And I think one of the reasons that these scaling approaches end up being problematic and not working very well in some cases, in a lot of cases in our experience, is that they really aren't thinking about size. They're thinking about agile, but they're not really thinking about the significant effect that generic size issues have, whether you're agile or not. And so understanding size and then coming back and applying that into your agile scaling efforts can be a very productive way to think about agile scaling among other topics. So let's then introduce size, and in part what I want to be clear about here is what I'm talking about. I think there are various ways of looking at size. One way is the size of the software itself, how big is the thing we're building, and the other is the size of the software project, software development effort, and so on. And even when we break it down that way, we can still break it down further. Certainly when we look at size of the software itself, then there are ways to look at that size, including stories and story points. So those are a couple different ways that we could look at size. In the older days, we might have looked at it in terms of lines of code. We still occasionally see organizations that are thinking in terms of function points. So these are different ways of measuring the size of the software itself, or looking at the size of the software itself. Use cases would be another kind of technique that would get used sometimes. And as I said, occasionally we still see organizations using some of these other ways of looking at size. We could also look at the size of the software project as opposed to the size of the software itself in terms of the cost or staffing level. Total staff in terms of staff months or staff years would be one way that you could look at how large a project is. Peak staff is another interesting one. On small projects, you don't tend to think about peak staff. You tend to have staff level loaded over the course of a project. But on larger projects, peak staff, where you started with a smaller staff, build up to a large staff, and then maybe roll off some staff before you even finish, that becomes a more relevant concept. And then cost is really a proxy for staff. The vast majority of cost in software project comes from effort or staffing, and so cost ends up being a proxy for staffing, or staffing ends up being a proxy for cost, depending on how you want to look at that. It's also useful to look at the duration of a project. Staff size is one thing, but how long the project is going to go is another thing. And these don't necessarily have the exact same effect on project outcomes. In fact, there's some significant differences. And these days, of course, we have lots of projects that are measured in weeks or days or even hours in some cases. But we still have projects that are measured in months. And every once in a while, we run into an organization still that has a multi-year plan for its project. Those are rare these days, but we still see those from time to time. So duration is another way to think about size. So those are the kind of background on ways we might think about size. Different of these aspects will come into play in different parts of the rest of the talk. So when does size become an issue for software? And here, let's review a common pattern that we've seen over and over in companies that we've worked with, and maybe this will be familiar to you too. Let's say that we have a small project that's been successful. That project might have 2 to 5 people using Scrum. The project has been successful, so naturally we want to get more of that goodness that we experienced in that small project. So the next thing we do is we have the project grow, and we add people to the team, and maybe now after a while we have 5 to 7 people using Scrum. And the project is still successful, the team is still successful, and so what happens next? Well, what happens next is that we launch additional projects, and each of these projects is about the same size, in that 5 to 7 people range. And we find that although some struggle, that overall, in the main, these projects are successful. And so we're feeling pretty good so far. We've added teams. The projects are still pretty independent from each other. They're all in this 5 to 7 person range, and things are going pretty well. Well, there comes a point where the company grows to a technical staff of, let's say, on the order of 50 people. Company decides to take on a major rewrite of its initial system. And this is one of the things that happens is you get a system that starts small, has a small team. Maybe you go for 2 or 3 or 4 years with a small team that's growing gradually, and you accumulate quite a bit of code over the years. So it started out as maybe a 1-team project. You didn't plan it as 4 years, but you've built up code over 4 years. Now when you take on this major rewrite, you're essentially taking on a 4-year project, but you don't want to plan it to take 4 years, so you increase the team size. So in this case, the company takes on this major rewrite, and maybe it staffs the project at about 20 people or something like that, because it doesn't want to take 4 years to redo the work that it did. So what happens here is the company struggles with how to organize work on a 20-person Scrum project, if they're still doing Scrum, which they probably are. And this is not super intuitive. It doesn't seem like you should necessarily add a huge amount of structure and overhead or go to a waterfall approach, but there are some questions about how you would organize a 20-person Scrum team. So the project gets underway, We do some requirements work or population of the product backlog in an iteration 0, but that takes longer than planned. And then we get into some architecture work because we have an awareness that we really ought to do some of that before we get started, but that also takes longer than planned. And so what we find is that the individual Scrum teams, if we've managed in this 20-person project to keep each of those teams to something like the idea of 5 to 7 developers, they experience numbers of dependency issues. And then the project ends up spending a lot of time figuring out how to coordinate the teams, and then more time actually coordinating the teams. And so this becomes frustrating because it feels like there's not that much time left for productive work. All the effort's going into coordination and not as much time is going into actually doing the work. And that is quite a contrast to what we saw with that original standalone one-person team. And so what we find is that the requirements issues, product backlog issues, misinterpretations of user stories, failed captures of user stories, etc., continue to cause rework throughout the project. We thought we were done with things. It met our definition of done, but we discovered that in some way or other it really wasn't done. We continue to see architecture issues that cause rework throughout the project. And in general, what we see is the project experiences significant code churn. And so this is a pretty typical pattern as companies scale up and move from one project team that's in that 5 to 9 team range or smaller, moving into teams that are larger than that. And so in this scenario, the project is ultimately delivered successfully. We get working software out of it, and it's reasonably high quality, but it takes 100% longer than originally planned and is 100% over budget. And I'm not just making up those numbers. Those are actually pretty typical outcomes when a company takes on a project that is larger than it's used to doing and doesn't really understand the ins and outs of size. And so that's an example of why I think size is such an important topic. And we've seen this kind of pattern over and over again in the companies that we've worked with. And as it says, this is the positive version of this story. The negative version of this story is that the project fails outright, gets canceled, team disbands, companies not able to actually perform work at larger sizes. I think that's maybe we've kind of seen a mix of these, but certainly there are cases where the overrun is far more than 100%. There are cases where the teams fail outright and just can't deliver software. There are cases where the defects become so prevalent that most of the work of the project goes into fixing defects, and there's little work that goes into moving the project forward in terms of functionality. So this truly is the positive version of the story. So let's go back in time a little bit. I gave you the kind of typical scenario for companies. Let's go back in time a bit and look at history of the world of software in relation to software size. If we go back to the 1970s and 80s, we saw that the mainframe systems of the 70s and 80s had already grown to be huge because that cycle started earlier than the 1970s and 80s. We had many programs that were under development for 10 plus years. They'd accumulated hundreds of thousands or even millions of lines of code. And so in the early 1980s, the microcomputer revolution happened with the IBM PC, and that led to programming in DOS. And what people found was that small DOS programs were easier to write than the mainframe programs had been. But we have to keep in mind that a lot of these mainframe programs had grown to be enormous. And so what we're really comparing is small DOS programs to enormous mainframe programs. By the time people had been working in DOS for a while, medium-sized programs in DOS were still started to become a little bit more of a challenge. And as PCs became more prevalent and we got into larger and larger applications or programs in DOS, large DOS programs became a significant challenge with a high failure rate. And the computing literature of the mid to late 80s and early 90s had all kinds of examples of microcomputer projects that failed because, in my view, because the companies were just not equipped to deal with large projects. They didn't understand the dynamics of size. When we moved into the early 1990s, we saw the pattern repeat with Windows as we moved from DOS to Windows. Small Windows projects initially were successful. As people started to rely more and more on Windows projects, we moved into medium-sized Windows projects. Those ended up presenting some challenges. Maybe they didn't fail, but they struggled to cross the finish line. As we moved into large Windows projects, which is something that happens over time as we move into new technology platforms, then these large projects again presented significant challenges, including a lot of failures. So we saw the cycle repeat. As we moved into internet programming, same basic pattern. Late 90s, early 2000s, the early internet systems began with small programs, which succeeded in many cases pretty easily. Medium-sized programs were challenging. Large projects struggled or failed. So the key point here, hopefully you're starting to see the pattern, is the issue is not DOS, it's not mainframe programming, it's not Windows, it's not internet, it's project size. And that's the key thing to recognize. And the general technology pattern is that a new technology emerges. Initial programs in the new technology are small, and they have to be small because they're greenfield projects. They're starting from scratch. The technology didn't exist before, and so of course they're small. Because the small projects are successful, these initial successes lead to attempts at larger projects. The medium-sized projects struggle, and then as we get into the larger systems, the large programs end up struggling significantly, and in many cases ultimately failing or requiring a massive reset where we have to go back and start over. And so I think it's good to be aware of this general pattern where we're going from small to medium to large, and we're going from largely successful projects to struggling projects to failing projects in many cases. So I think some aspects of this pattern end up being kind of counterintuitive, and the way in which they're counterintuitive actually is because of the influence of size and reflects back on just how important size really is. So if we look at how technology matures over time, if we start out with a new technology, in a lot of cases, the development environments are actually pretty unstable to start with. And as time goes by, the development environments become more stable and become more feature-rich, more reliable, and so on. We end up having fewer bugs attributable to the technology itself. A lot of times, early technology is itself buggy. You follow documentation, it doesn't work, takes you a long time to figure out. It's not your problem, it's actually a bug in the technology. As time goes by, the documentation becomes more accurate. We can rely on it better, becomes more extensive. There are more posts on the internet of other people who've tried to do the same thing you're trying to do, so you have more resources to look at. There's better training support. As time goes by with new technology, there become more resources available in person or virtually or recorded that explain how to use the new technology and are actually reliable. And also there's better consulting support. The consultants have had time to get up to speed on the new technology, see other companies working with the technology, learn the do's and don'ts of the technology. So all these factors collectively should say that as technology matures, it should become easier to do work in that technology. The longer the technology exists, the easier it should be to do effective work. And what we really should see is a curve like this, where in the early days of a new technology, we have quite a bit of difficulty. As we get into the later days of the technology, we get more maturity, and the difficulty is actually lower than it was in the early days. So that's the pattern that we should see. But what we often see is that as the technology matures, there's another factor in here, which is the average size of systems is in play, and size goes up over time. And that means that the difficulty actually increases over time when the technology maturity says that the difficulty should be decreasing over time. So this is another example of how the size factor actually ends up usually dwarfing the technology maturity factor as an influence on software project outcomes. So let's look at a few more size-related dynamics. In a way, these will be variations on a theme of what we've already talked about. Actually, I take that back. These are not variations on a theme. These are a few of the factors that contribute to the difficulties that we've seen in size. When we look at error rates, one of the counterintuitive aspects of size is that the larger code base becomes, especially during its initial development, the higher the error rate becomes as we work on that code base. And in this case, the vertical axis is defects per 1,000 lines of code, and the horizontal axis is size in 1,000 lines of code. And so what you can see is that although it's possible to have pretty low defects at almost any size, when we get into the average level of defects, the average amount of defects increases dramatically that is not the amount of defects, the rate of defects increases dramatically as size increases. And of course, the top end increases really dramatically in terms of the error rate. And I want to be clear, I'm not talking about the total number of errors produced, which would just be a linear function of size. I'm saying that the rate increases as size increases, so the overall number of errors increases in a nonlinear way or disproportionately compared to the size of the thing that we're building. If we look at productivity by size, which is a related dynamic, here we've got lines of code per staff year on the vertical axis, and we've got the size of the system in thousands of lines of code on the horizontal axis. Here, the productivity by size drops dramatically as we increase the size of the project. And it's pretty interesting here. This is not a case where the average productivity is right in the middle of the curve. This is actually a case where the average productivity is always quite a bit closer to the worst productivity than it is to the best. In very small projects, we have some really exceptional top-end productivities, but when we get into large projects, even the top-end productivity is pretty constrained and is not going to be that significant. The average productivity ends up being a pretty straight decline in terms of the average, the amount of output per staff month or per staff year. And so the amount of code that each individual staff member is producing decreases significantly as you get into larger size projects. So just to be clear about how the numbers work here, if we have a really small system, we can see staff outputs on the order of 25,000 lines of code per year per staff member. By the time we get to really large systems on the order of, this is 10,000 KLOC or 10 million lines of code, so this is very large system indeed. The top end productivity is around 5,000 lines of code per staff year, and that's best case. The average case is more like 1,500 or 2,000 lines of code per staff year when you factor in all the staff that are working on various aspects of the system. So productivity drops significantly as size increases. And then the impact of all this, now these are just two of the factors that influence project outcomes, but you put those factors together with some other factors, and what we find is that project outcomes worsen significantly as we get into larger size systems. So if we look at the very smallest system and you look at the green area on the screen, for really, really tiny systems, and these are essentially like one person, very short-term initiatives, these have a very high chance of being successful and delivered on time or early. When we get into medium-sized systems, we start to see a higher percentage of late and failed projects, and this is still not very large. When we get into now medium-sized systems, so this is 50 to 100,000 lines of code or 1,000 function points, now we've still got a better chance of being on time or early than not, but we have on the order of 10% of projects failing outright, on the order of 15% of projects being delivered late. By the time we get into what I would start to call a larger project, around 500,000 lines of code or 10,000 function points, now we've actually got more than a 50% chance of delivering late. It's the exception that the project is going to be delivered on time or early, and we're starting to see a significant percentage of projects that fail outright, meaning they're canceled without delivering any usable functionality. So we've got about 25 or 30% of projects that are actually failing. By the time we get out to the very largest projects out here, where we've got 100,000 function points or 5 to 10 million lines of code, more than half the projects are failing outright at this size level. And so our primary concern at this size should be finishing at all. And a lot of times we see companies worrying about efficiency at this size. Efficiency is the last thing you need to worry about. I mean, you should think about it, but the first thing you should worry about is making sure you're actually going to finish, because such a high percentage of projects don't. And so what are the factors that contribute to this? Well, we've got the lower productivity that kicks in due to size. We've also got the higher error rate that kicks in due to size. There's an interplay between higher error rate and lower productivity. The higher error rate leads to lower productivity, but it can also just lead to problems in finishing at all if the errors get away from you. So what we find, to go back and put a ribbon on the package of this technology pattern of moving from small to large projects over time, is really that the technology is a little bit of a red herring. Small projects are relatively easy, almost regardless of the technology. Large projects are relatively difficult, almost regardless of the technology. The exception here is if we really tried on day one of a new technology to do a massively large project, which hardly anybody ever does. But if we did try to do that, we would find, in fact, that that's more difficult than doing a large project in a mature technology. But it doesn't tend to happen that way just because of the way companies move into new technology areas. So now let's take a look at some other common size transition patterns. And I think these will seem a little bit like variations on a theme, but I think it's useful to point out the other ways that this size transition comes up. I think we see that as companies grow, they typically start doing larger and larger projects. If your software does well and your company does well because the software is doing well, just the nature of the beast is that the software is going to grow over time. We don't see companies start out with a huge code base and pare it down so it's small over time. No, we find that companies find more ways that they can use the software, more other systems they want to interface with, more capability needs to be added, and so the software grows. And that means that as the company grows, the software grows, and the larger projects will struggle more than the smaller projects did. So it's pretty common for companies, for kind of mid-stage companies, who were successful in the early days through kind of brute force approaches to software development. They hire smart people. They, everybody works hard. They're highly motivated. Early projects seem to succeed pretty well, but these mid-stage companies tend to get to a point where the projects become large enough that simply having smart, highly motivated people is not enough to make the large project successful. And at that point, the company starts to struggle. We also see this in established companies that do pilot projects in a new area. Pilot projects, by their nature, tend to be small. That's really the definition of a pilot project. But if the pilot project succeeds, if it proves whatever it was supposed to prove and shows that that can be successful, successful pilots tend to lead to a larger scale rollout. And then the larger scale rollouts are often problematic because the company does not account for the difference in size that comes up or that changes between the small pilot and the larger scale rollout. And so companies will often misdiagnose the problem. They'll say, well, our pilot didn't fully show all the issues it needed to show, or that kind of thing. Well, in a sense, that's true. The pilot didn't show issues related to size, but the key factor here really is size in general, not the pilot specifically. And we've seen this new technology pattern, and I include it here really just for sake of making sure that it can be included in the list. But I think we continue to see the same pattern repeated over and over again. So internet development, more recent days, mobile development, cloud development, et cetera. Whether it's machine learning or artificial intelligence, anytime we get into a new technology, we're going to see this same kind of pattern. Methodologies is another way that this shows up. If we have some new methodology, 20 years ago, Scrum was a new methodology. 10 years ago, Kanban was a new methodology in software. If that does well on small projects, then we naturally want to take some of that good results that we're experiencing on small projects and apply it to large projects. And at that point, the challenges increase. The increase is in part because large projects are just, generally speaking, more difficult. And that's really where we are with Agile today, where I think we're starting to see a little bit more success with SAFe than we were seeing a year ago, 2 years ago, 3 years ago. But large projects are still problematic. And I think none of these scaling frameworks are really all that great because I don't think any of them really address size per se as the main issue. It's all about Agile, not about what are the general issues in scaling that we want to address, because we have to address these general issues. And by the way, we want to remain as agile as we can as we scale. The first order of business is scaling, because that's the thing that determines whether we'll complete the project at all. And then the second order of business is trying to keep some agility there. I think we often end up I think these other frameworks tend to put the cart before the horse in that respect. So let's now talk about the critical issue of the nonlinearity of software size issues. And I need to wave at my motion detector here. My office lights turn off automatically after a while. And so what we find is that I think the most common misunderstanding about size is that a large project is just X number of times a small project. If the large project, let's say we've got a small project with 5 people and we have a large project with 25 people, you naturally think, well, it's 5 times as big, so we need to do 5 times as much work in different areas. A lot of times people even make a more off-base assumption, which is, oh, we'll get some advantage, and so it won't be 5 times as much because we'll probably get some efficiencies of people working together. And this is exactly dead wrong. What we find out is that some attributes or challenges and activities in software projects scale linearly, but some attributes scale non-linearly, and they don't scale in a way that gives you increased efficiency. They scale in a way that gives you decreased efficiency. And so if there's one takeaway from this talk that I would ask you to take away, it's that as you scale your projects, be aware that there are issues that scale in a non-linear way. You can't just multiply X times Y and think that's a good plan for your larger project. So at larger scale, some examples of challenges that emerge are, well, these are examples of larger scales: growth of the company's software, large rollout after successful pilot projects. We've really talked through these already. And I think the important thing to remember is these are not just bigger lifts of the same thing. It's kind of a different kind of lift in addition to being bigger. And I think the key point here is that if elements of the problem scale non-linearly, then elements of the solution need to scale non-linearly too. And if we can understand how the problem scales non-linearly, that can help us come up with some ideas about how the solution needs to scale non-linearly. And I'll get to that a little bit later in the talk. And so there's this notion in software of what's known as a diseconomy of scale. We don't use the word diseconomy very often in common speech. We talk about an economy of scale, which is the idea that if we have a small auto manufacturing plant and we build a larger auto manufacturing plant, our cost per unit might go down. That's the concept of an economy of scale. In software, we don't get an economy of scale. Unfortunately, we get a diseconomy of scale. And what that says is that as the projects get bigger, our unit cost goes up. So we have higher unit costs with larger projects, meaning that, and now what that implies is per person productivity decreases. On a small project, a specific individual might be able to produce 10,000 lines of code per year. On a large project, that very same individual might be able to produce only 5,000 lines of code per year. It's not because the person has become a worse programmer, it's because large projects have a diseconomy of scale and per person productivity decreases. So to show this graphically, if we didn't have a diseconomy of scale, if we had unit cost and project size, then unit cost would stay exactly the same over the entire course of the project if there was no diseconomy of scale. What we have in software is not just an increase in unit cost, which would be linear, shown as a straight line going up, not flat, but we have what's an exponential diseconomy of scale, meaning the bigger it gets, the disproportionately quickly the diseconomy of scale kicks in. Now, this green line is a very exaggerated diseconomy of scale. It's nowhere near that severe. It actually looks more like this, where we've got a fairly mild exponential effect on diseconomy of scale. But the key point is that it does in fact increase non-linearly. Now in this graph, the green line is actually curved, but it doesn't really look curved because the curve is so mild. But the key point is we've got a diseconomy of scale, and it actually increases slightly exponentially. So that's kind of the traditional explanation. I think an easier way to look at it, and in my experience, the way that makes more sense, is to look at diseconomy of scale as a step function. And I think an easy way to look at this is that it's essentially about coordination overhead. I mean, this is not intended to be pejorative, but you could look at it as you add layers of management to the project and layers of coordination, that is the diseconomy of scale, the addition of the management and the coordination. Depending on the nature of your project, the specifics of the coordination could be management, could be requirements, could be architecture, could be process. And I think it's important to understand that those are not the same in every case. And that's one of the reasons I think that generic scaling approaches, especially in the Agile world, don't do that well, because in some projects, the scaling is about process, but I think that's the minority case. More often, I think the scaling has to do with requirements. That's probably number one, I would say, is the requirement scaling is probably the most common source of challenges, or that scales, the coordination scales non-linearly. Second most common, I would say, is probably architecture scaling. Management scaling is always in there to some degree. Process scaling is always in there to some degree. But this is going to vary. Your project, it might very well be that management is the thing that needs to scale, and maybe requirements is last on the list. The point is, the specifics are going to depend on your specific project. The thing that's probably going to scale on virtually any project is higher defect rates. That implies increased defect correction effort due to the factors above, basically due to mistakes made in the factors above. And so this economy of scale comes from all this kind of coordination overhead, plus the defect work. If I don't know if you want to call that coordination overhead or not, but it's overhead in a sense. And I think the diseconomy of scale in software, what I see is that it's more of a step function than a smooth linear curve. And the steps really come in at the sizes at which additional levels of coordination need to be added. If we have a 5-person team and we add a 6th person, we're probably not going to add an additional level of coordination because we have a 6th person. We're just going to have somebody do a little bit more coordination work rather than adding a whole different level. What we tend to see instead is that we tend to add levels of coordination at roughly powers of 7. So if we have a team up to about 7, we can have one leader of that team or a scrum master, or have it be self-managed. When we get up to the next power of 7, which would be officially 50 or 49 rather, but we'll round it to 50. At this point now we have multiple leads, multiple scrum masters. We start to have specialists in various areas, could be user interface or data scientists or database. But we also need people to coordinate the leads and coordinate the scrum masters. So we get a group manager, we get an architect in addition to a design lead, we get a director, and so on. When we get to the next power of 7, which would literally be 343, but in round numbers, this comes up in organizations, we tend to see it show up at lower sizes, probably closer to the 250 range than the 350 range. Now we actually have to add additional coordinators that are essentially like the dev managers, the test managers. Maybe we don't even just have architects anymore. We've got chief architect, and we have directors, and maybe even a VP sitting on top of that organization. And so I think what we see as organizations, as they grow, they tend to have some points of discontinuity here where they need to reorganize because they've grown and add new levels of coordination. And that's where I think the diseconomy of scale really kicks in. So I should also point out that it's not just the amount of work that needs to be done as we get into larger projects. The kind of work also changes as we get into larger projects, and the ratios of how much effort we're spending on different kinds of work also change. So here's my diseconomy of scale as a step function. Productivity, shown as a red line, decreases, but it doesn't decrease as a straight line. It decreases at specific points where we're having to reorganize to add additional layers of coordination. And what that means is that output, total output, increases in a jerky fashion as well, where when we hit that point where there's a step function, we also hit a related point where, because we're adding coordination but not adding staff that are actually doing work at that size, we actually have I think we have a decrease in total output at certain sizes. And so these are actually kind of tricky points to be at, because we were kind of taking a step backwards when we hit this step function so that we can take a step forward and get to a higher level where we actually increase output. But there can be a zone here where the total output actually has not increased even as we increase staff size. So, and I think that, as it says on the slide, one implication of this is that it's less risky to increase team sizes within certain ranges. If we can stay within the range where we don't have to take the next step, then that's actually a safer place where we can add staff. But when we get to the point where we really do need to add the coordination overhead and maybe break people into multiple teams, that's where we start to experience steps, and we have incremental increases that might not lead initially to incremental increases in output. All right, so this has all been background, hopefully useful background on understanding some of the dynamics of size, the reasons that size is challenging, and the specific ways that size presents challenges on projects. I'd like to turn now to a couple of thoughts about attacking size, and I'll give you basically 3 ways to think about this. The holy grail of large projects is to break your large project up into a series of small projects. Or it says series, it probably should say a set of small projects. These are not being conducted end to end, they're being conducted in parallel. And we have this notion of the ideal being that we could partition the work of a large project into a parallel series of small projects. And this is ancient suggestion going at least back to the Mythical Man Month published in 1975. The issue we run into is this issue of Conway's Law, which says that the structure of a system will reflect the structure of the organization that built it. And for this parallel small project strategy to work, the small projects actually have to be truly independent of each other. They have to be actually partitioned, that is, not dependent on each other. The more they become dependent on each other, the more they start to behave like one large project instead of a bunch of small projects. And so this is a place where software architecture actually comes in, because the structure of the system at the architecture level is going to partly determine what the human organization looks like and how efficiently the human organization can operate. And so we have to be aware of Conway's Law as we scale up and as we try to partition the large projects into parallel small projects. This is problematic these days because software architecture is something that is actually, in some cases, deprecated by Agile practices. And it means that we actually have to do the software architecture work before most of the human teams are staffed and organized. And sometimes we run into a cultural issue on Agile projects because Agile teams sometimes say we don't really want to do that much architecture. I do feel like the pendulum has swung some in the last few years. We see more and more Agile teams that are accepting the idea of the need for architecture work, especially as they've run into the problems that happen when you don't do that. But I think some organizations, we still see a cultural pushback on the idea of doing architecture, when I think that actually is a necessary activity to be successful with larger projects. So even if we can get past the cultural issue, then of course it's still challenging to do architecture well, but I think it's still worth attempting so that we can use architecture, part of course just for this pure software benefit, but also part for the benefit in organizing the work on a large project in a way that's going to reduce the dependencies and help us streamline that large team. We're never going to get to the holy grail of completely partitioned, or we'll rarely get to the idea of completely partitioned work where we can have partitioned teams working truly as independent small teams. But I think it's useful to try to push as far as we can in that direction. The second idea that I want to present in terms of attacking size is understanding the specific sources of nonlinearity. And I think an interesting lens to do that through is the Kokomo 2 estimation model. If you've heard me talk before, you've probably heard me talk about Kokomo. I'm not a huge fan of the model for its intended purpose, which is estimation, but I do think that the statistical analysis work that's gone into isolating the effects of different factors on project size is probably the best statistical work that's been done in the industry so far. And so in Kokomo, what we see is that the biggest influence on outcomes is product complexity. And what this, the way that this gets interpreted is that this says that all other factors being equal, including size, meaning size in lines of code, if you have a high complexity, the highest complexity project, that can increase nominal effort by 74%. If you have the lowest complexity project at a particular size, that can decrease nominal effort by 27%. You interpret these other numbers the same way. Now, I'm not going to go through all the factors on this list, but I will call your attention to the factors of precedentedness, process maturity, architecture and risk resolution, development flexibility, and team cohesion, the factors shown in red or orange on your screen. Most of the factors in Kokomo affect project outcomes linearly, meaning it doesn't matter how big your project is, the percentage factor is the same. But for these factors that are shown in red, these affect project outcomes non-linearly, meaning the bigger the project becomes, the higher the impact is. And so in this example, I have to show Kokomo factors influence from the point of view of a particular size, a small project. In this case, this is 100,000 lines of code. Now, it may or may not be small for your organization, but at this specific size, precedentedness can increase your outcome by your effort by 15%, or it can reduce it by 19%. Precedentedness refers to how familiar is the application you're working in. Is it precedented or is it unprecedented? Process maturity can increase your effort by 15% or reduce it by 19%, and so on. Now, what's interesting about this is if we change this graph and look at it from the point of view of a large project, in this case, 5 million lines of code, look what happens to these red bars. Now, the small project, none of the red bars are in the top half in terms of influence. But when we go to a large project, every scaling factor, every nonlinear factor is now in the top half in terms of influence. So precedentedness, for example, just to pick one, which went from -19 to +15%, is now from -33 to +30% in terms of its effect on the overall effort on the project. And I think this is pretty important, because what this says is that the factors that matter on small projects and the factors that matter on large projects are not, in fact, the same. So, if I have a small project, I don't necessarily have to focus a lot on process maturity. It's not in the top half of factors. I don't necessarily have to focus on architecture and risk resolution. It's not in the top half of factors. But if I continue that approach on my large project, now all of a sudden, I better be focusing on process maturity because it is in the top half of factors. And I better be focusing on architecture and risk resolution because that now is in the top half of factors. And so when organizations scale up, they often don't understand how these things change, and that leads to problems. Ordinarily, when organizations experience challenges on larger projects, they just try to repeat the practices that made them successful on small projects harder with more commitment or with more fidelity. This is a very intuitive and natural response, but it just doesn't work because the factors that matter have changed. The rules of the game have changed. You've got to focus on different things at that larger project size. So I like this phrase, what got you here won't get you there. And I think that applies very much to this idea of success on small projects doesn't really prepare organizations to succeed on large projects because the success factors are not the same. All right, the last tool I want to share for understanding nonlinearity of activities today is intellectual phases. For those of you who are able to attend the Lunch and Learn session earlier this week, we talked about that quite a bit. I mentioned earlier in this talk that if the challenges scale nonlinearly, then our responses or solutions need to scale nonlinearly as well. So how do we go about thinking about that? If we're going to scale activities like requirements, architecture, construction, system test, how do we know which thing we need to emphasize more? And how do we know how to scale overhead roles like product owner role, scrum master role, architect role, other roles, and so on? Well, the answer, of course, is it depends because everybody's circumstances are different. I think one of the fallacies of generic scaling frameworks is that the bigger the project gets, the more unique the circumstances become. And so while generic solutions can apply pretty well in small project sizes like generic Scrum, when you get to large project sizes, you get so much uniqueness that it's really hard to come up with generic solutions. In fact, I think it's a futile effort. So the general pattern of project activity mix by project size is that what we think of as the core activity in software, construction, is the main activity at small project sizes, but when we get out to larger project sizes, it isn't a majority activity anymore. We actually need a lot more effort put into system test. We need a lot more effort put into architecture, a lot more effort put into requirements. So if we keep trying to do the same ratios of activities, generically speaking, then we're just not going to do enough of some of the upstream activities or earlier activities on larger projects. So that's one way to look at it. But the question is, well, how much? How much do we need to scale our focus on these activities? And is it more like heavy emphasis on requirements and architecture, or is it more of a heavy emphasis on system test and construction as we scale? Well, again, the answer is it depends. And I think the one thing that we can know for sure is that we're not just going to scale everything proportionately. So how do we know how to scale it disproportionately? And here I think we go back to this intellectual phase view of project scaling challenges. And if this is not familiar, you might take a look at the lecture from earlier this week, which is recorded and available in our Construx On Demand platform for free if you want to look at that. But I think a way to think about this is the variations we went through on this earlier in the week, which is if you foresee your challenges coming mainly in the discovery area, that's where you need to scale disproportionately. If you see your challenges coming disproportionately in the invention area, that's where you need to scale disproportionately. If you see your challenges coming primarily in the construction area, then that's where you need to scale disproportionately. And all the permutations are possible here. If your challenges are mainly going to come from discovery and construction, then those are the two areas where you focus your disproportionate scaling. And the same logic applies to these other permutations. So I think that gives us a useful tool and a useful way for looking at how we could at least begin to think about project size and how we attack challenges arising from project size. You know, in some level, you'd think the details of size might be obvious and that maybe a smart person could just figure out the differences. But experience really says this is not the case. Experience says we've got tons of smart people working in the software industry, and the success rate of large projects is much lower than the success rate of small projects. So I think the details of size are not, in fact, obvious. And I think it's important to understand the idea that what got you here won't get you there, that small project success does not prepare companies for large project success. The success factors for large projects are different, and that a lot of the details in software are non-intuitive or counterintuitive. So understanding these project dynamics can make a big difference. If you like this stuff, I'd encourage you to check out my other lectures from the Understanding Software Projects lecture series, where I talk a lot more about the 4 factors lifecycle model. We will have additional lunch and learn sessions. Some of those will be on the 4 factors lifecycle model. Some of them will be on other topics. The ones we have coming up next week are much more focused on agile practices. We have one coming up on specifically these days on agile practices for people who are working from home. So we have one topic coming up next week on how to use user stories in a way that supports people working from home, and another one on how to scale, or not how to scale, but how to adapt the Scrum Master role so that it works effectively when the team is distributed and working from home. So at this point, I think we've got a couple minutes left, and I'm going to take a look at the questions and see what we've got here in terms of questions. Let's see here. Yeah, so good question. What do you consider small, medium, large, and whatever units you prefer? I think this is an especially good question because this answer varies so much from one organization to the next, and it very often the case one organization's small project would be considered by another organization to be the largest project it ever does. You know, that's one advantage of my company is we've worked with so many different organizations over the years that you see every variation, and this is one where if I'm talking to a specific company and they say we had a large project that struggled, I do in fact have to ask them, okay, what do you mean by large? How big was that in terms of staff size or duration? I think for our purposes in this discussion today, large just means whatever's bigger than the size of project you normally take on. So if your company normally takes on 2-person projects and you're now taking on a 7-person project, that could very well constitute large for purposes of the discussion today. And that's kind of an endpoint or an end case, but I think that would qualify. If your organization is maybe more typical and you've got a lot of 3 to 7-person projects, then I think large probably comes into play when you have to do a multi-team project. If most of your projects are single team projects and you start to do a multi-team project, and that's the exception, then I would say that's a large project in your organization. So the answer really is larger than usual. All right, so next question here is, let's see. It says, Steve, do you think in some cases a project using, for example, or it says a company with poor design and architecture or poor development testing practices can find that an easier solution is throwing more people at the problem? Do you think that is the case, that some projects employ large numbers of developers as a way to compensate in numbers for their deficiencies in software engineering practices? I think that's an interesting question, because I think that is a pretty common approach, that we throw more people at it. You know, the people who are throwing more people at it never think they're just throwing warm bodies at it. They always think they're throwing qualified people at the problem. But I do think that comes in part from not understanding issues related to scale. And there are a lot of circumstances where adding people to the project is in fact going to make the project slow down and have less total output. And it's not very intuitive why that might be. But I think I've made comments throughout the Lunch and Learn session today that give you some insight into why, in fact, you might actually reduce total output when you throw more people at the problem. I know a lot of times, one of the truisms in software that I wish wasn't this way, but it really is that in software you get penalized for being bad. And if you start out on a good footing where you've got good plans and a good understanding of what to do on your larger than usual project, then you have a higher chance of that project being successful. You're also going to build in earlier opportunities to course correct for yourself, and lots of opportunities to make sure that your things are working as well as you expected, and have them ultimately work out successfully. If, on the other hand, you're less competent when you start the project, you're probably going to start it with not enough of the right kinds of activities in place. You're going to let time go by. You're going to do work in really what ends up being some of the wrong areas. And by the time you realize that, so much time has gone by, it's really too late to fully correct for the problem. And so in essence, you get penalized for being bad. And that's just the way it is in software. So the more you can understand these issues up front, the more you can understand your projects and set them up for success in the first place, the more successful your projects are going to be. And that really is the purpose behind my Understanding Software Projects lecture series. Is I think an awful lot of projects struggle unnecessarily, and with a better understanding of where those struggles come from, a lot more projects can be successful. I think we're going to have to leave it there for today. Thanks everybody for joining us. We will have more sessions throughout the rest of March and into April, so please go to the URL shown on the screen, and please invite your friends, and thanks for joining us.